Hey guys, this video is covering chapter 13 of your Marshall Cavendish textbook. After this video, as part of your June holiday homework, you are required to do worksheet 13 from your theory workbook and to pass it up on the first day of school. Now, the notes for this can be found on your Google Classroom, so please do download the notes before you proceed with carrying on watching this video. So what are you going to learn today? Alright, from the video today, you're going to learn what on earth is wave motion. Alright, you need to be able to understand how waves transfer energy and at the same time without the transfer of the matter or the medium is traveling through. You also need to be able to state differences and similarities between the two main categories of waves, which is longitudinal wave and transverse waves. And for each of these type of waves to be able to provide an example of each of them. Now, waves are pervasive in all aspects of our life, even though we may not necessarily see it. It's used in a lot of tech. You see it in water waves, even light that allows us to see travels as wave. So what exactly is a wave? Alright, so a wave basically is a disturbance that transfers energy from one point to another. Alright, waves are periodic in nature, so that means the waves will move at regular intervals. You can predict where it will move, what kind of motion it will have. So an example of something that has a periodic motion that you've already experienced is a pendulum, because as you know, a pendulum will move back and forth and back and forth. So just to remind you, one back and forth motion, a full one back and forth motion is called one oscillation. Alright, so what are some defining characteristics of waves? So to do that, let's talk about waves in the rope. So for example, if I have a rope tied off to one end of a wall and the other end is being moved up and down, you can see that actually this disturbance or the wave is actually moving from one point to another. So the energy is being transferred from left to the right. But what is important for you to note is that the particle, or actually the rope, doesn't move together along in the direction of the wave. That means the particle doesn't move left to right. That particle or that portion of the rope actually just moves up and down as the wave moves. So this is two of the defining characteristics of waves. One is that energy will always be transferred from one point to another, and second, that the medium that is traveling through does not move together with the wave. Instead, it moves in its own oscillation. Another example, waves in the ripple tank, or just basically just water waves. If I were to put a dipper or to disturb the surface of the water with something like a stick, and I just move it up and down, you can see that actually the wave moves away from the source of the disturbance, but at the same time the wave particle actually does not move along with the wave, it just moves up and down. So again, the two characteristics: energy moves from one point to another, but the particle doesn't actually travel or transfer together with the wave, it does its own oscillation. So, in summary, the two important characteristics of waves is that they transfer energy. I believe this is the third time I'm repeating this, but it does not transfer the medium with the energy. Alright, and usually, not necessarily most of the time, but usually the source is usually a vibration or oscillation, or basically a periodic motion. Alright, to allow you to get a better visualization of what a wave looks like, just imagine that I have a wave moving through a medium. All these black dots represent the particles of the medium through which the wave is traveling through. So if I were to observe on just focusing on just one particle, you can see that it does its own up and down periodic motion, while actually the wave is transferring the energy from left to the right. If you follow the top part of the wave, it's moving from left to the right. So this kind of waves is called transverse wave, and we'll delve into that a little bit more. Another type of wave is called longitudinal wave. If I were to look again at just one particle, observe the red spot, you can see that it does its own periodic motion. Alright, just left and right, while the wave, if you have to follow, is moving left all the way to the right. Alright, so what it means by the medium is not being transferred along, my medium does not follow this wave as it moves along from left to right. Instead, it does its own periodic motion left and right, or either in the other example, up and down. So a good physical way for us to imagine what we just saw just now is to imagine a slinky. So if you fix one end of a slinky and the other end is free to move, and you move it up and down, then you will actually, if you imagine it, the wave or the disturbance will move from this hand that is able to move all the way to the fixed end. That means from left to right. But if you focus on only one spot of the slinky and you note the position of the slinky, then you realize that actually this slinky portion just moves up and down, up and down. Alright, another way that you can imagine this, the other type of wave, again we'll go into what transverse and longitudinal waves are. If I were to fix this end, and instead of moving it up and down, I move it left and right, left and right, left and right, you can see that the disturbance will move from the free end all the way to the fixed end. But if you were to just focus on one portion of the slinky, this same portion, if you track its motion, it will just move right, left, throughout its motion. So the particle or the slinky or the medium doesn't actually move all the way along. Alright, so it just conducts, or it just moves in its own periodic motion. Alright, so the two types of waves we introduced, I mentioned this just now, transverse versus longitudinal wave. So how are they different? Transverse waves. Transverse waves are waves that travel perpendicular to the direction of vibration of the medium. So this is important for you to know the definition. A lot of students get this portion wrong. They can't tell me the direction of vibration of the medium. So the important and defining one is that it moves perpendicular. So some examples of transverse wave that we see are water waves and any of the electromagnetic waves. So things such as radio wave, microwave, infrared rays, visible light, ultraviolet, X-rays and gamma rays. These are examples of transverse waves that you can use. That means when my wave energy moves from left to right, my particle is actually moving up and down. So it moves perpendicular to the direction. So wave energy again moves left to right, while my particle only moves up and down. So in this case, it's perpendicular. Alright, so the other example are longitudinal waves. So longitudinal waves, it's important for you again to know the definition, are waves that travel parallel to the direction of vibration of the medium. So imagine this, my wave particle or the energy is moving from left to right. Well, if I just focus on one part of the slinky, then the slinky does its own left and right periodic motion. So in this case, it's traveling parallel to the direction of the wave. So this is important for you to know, parallel. So an example of this kind of wave is sound. So there are other types of longitudinal waves, but for the O levels, you only need to know sound. So going into an example of what a question could be, so just have a look, describe and explain the motion of a styrofoam ball when the rod is dipped quickly into the water and then removed. So if you, in case you forgot, water waves are actually transverse waves. So if I have a dipper or a rod and I move it up and down, the wave energy will actually move from left to the right, and it will start disturbing the styrofoam balls. So that's what the styrofoam balls do then, they will move in a periodic up and down motion. So again, the wave energy moves from left to right, while the styrofoam ball move up and down. So perpendicular, that means it's transverse waves. Alright, so the next portion will be covering some properties of waves. So you need to be able to define certain quantities and identify certain quantities related to wave. So such as speed, frequency, wavelength, period, amplitude, and wavefront. And also be able to apply two formulas, the V equals to F lambda. So we'll introduce these formulas in this portion now. So first thing first, when we look at a wave, there are two things that we can identify easily: the highest points and the lowest points. So the highest points in a wave is called the crest of the wave, while the lowest point in a wave is called the trough of the wave. So if I look at this question, then simply the highest points here, here, here are the crest, while these two portions here are called the trough of the wave. Now, the next thing, physical quantity that we need to be able to easily identify when we look at waves is the amplitude. So, just to refresh your memory, we just said that a particle moves up and down in a periodic nature, or left and right, depending on whether it's a transverse wave or longitudinal wave. So, the particles, if there is no wave, is at a certain position, but when the waves moves through it, then it does this periodic either up and down motion in transverse or left and right motion in a longitudinal wave. So the maximum displacement from its rest position is called its amplitude. So if I have nothing going through, all my particles or my rope particles will be here, but because suddenly I have the wave moving through, my particles are disturbed to a certain position. So the position where it's maximum displaced, that is called the amplitude. Now, you may see this later on or in some questions, although it's very rare for you to see it now, but 2 amplitudes is equivalent to peak to peak. So what it means is 2 times the amplitude is the distance from one peak, the highest peak, to the lower peak. So that's why it's called peak to peak. Sorry, it's not 2, it's peak to peak. Alright. Now, it becomes useful also for us to be able to describe points on a wave that are in phase. So what are some characteristics of points in a wave that are in phase? Means they have the same direction, they are moving at the same speed, and they are the same displacement from their rest position. So imagine I have a transverse wave moving from left to right. Now, it is easy for us to do now the third point, displacement from the rest position. I can identify easily that this is at the maximum displacement, this point S is also at the maximum displacement, and this point V is also at the maximum displacement. So all these 1, 2, and 3 fellas are at the same displacement from their rest position, but the direction and speed is slightly tricky for us to identify. So to do that, and it's quite common in O-level questions for you to have to do this, is to draw a wave that has been slightly displaced. That means you imagine the wave is moving left to right. So in the next instance, then the wave will actually be in this position. So again, I say, just draw a wave, this whole wave, the original wave, just move it a little bit to the right because it's moving from left to right. And from here, you can identify easily where the particle actually moves. So if I were to focus in on P, you will see that in the next instant, this P is actually moving down. Remember again, transverse wave, the particle moves up and down or perpendicular to the direction of the wave, which is left to right. So if I were to look at Q, then I know that Q does its own up and down motion, and Q must now be at this position over here for the wave to move left to right. R moving to this position, S moving down. So if I were to look at all the points P, S, and V, then it becomes obvious that they are moving in the same direction. P is moving down, S in the next instant is moving down, V in the next instant is also moving down. Right, the same goes with R and T. R is moving up, U is also moving up to its next periodic position. So the points on the crest and the points on the trough are easy for us to identify where they are in phase. So R and U meet the qualification of a wave of points that are in phase because they're the same direction, the same speed, and the same displacement. Now, it becomes tricky when we talk about points nearer to the rest position. If I look at Q, there are a lot of points on the wave that are in phase with it. Oh no, sorry, not in phase. That have the same displacement from the rest position. If I look at Q, then this point here is also actually at the same displacement. Same goes with this point, same goes with this point, same goes with this point. Basically, all of these points are not disturbed from their rest position, so they have zero displacement from the rest position. But this point and this point are not in phase, and this point Q and this point is not in phase. So if I were to look at it at the next instant, again using the same method, at the next instant Q is moving up, but this point here, if I look at it, remember it moves up and down, it's actually going down. So Q is moving up while this point here is moving down. So this does not meet the definition of points that are in phase, because for them to be in phase, they must be moving in the same direction. So a bit tricky one, only Q and T are in phase, while this point here and this point here are in phase because they are moving in the downwards direction. Q and T are both moving upwards, so they are in phase. Now, because we have already discussed what it means for points to be in phase, I can now introduce the definition of a wavelength. And a wavelength, written as the symbol here, is the shortest distance between any 2 points in phase. By the way, this is the Greek symbol lambda. Alright, so it's the shortest distance between any 2 points in phase. So that means between P and S, that is the wavelength. Even though P and V are in the same phase, this is not the shortest distance. P and S is. Same goes with R and U, and Q and T. Remember, Q and this point, even though this is the shortest distance, they are not in phase with one another. So this is the shortest. So this is what we define as the wavelength of a wave. Now, waves are often described using two ways: displacement time graph and displacement distance graph. So for a displacement time graph, you can imagine it is us focusing on just one particle and tracking its motion over a period of time. Alright, so if I have a transverse wave and the wave is moving from left to right, I just focus in on point P. Point P will do its own periodic up and down motion. Alright, so all I need to do is to track the motion and display it on the displacement time graph. So this is what a displacement time graph will look like for a wave where I track just one particle over a period of time. It will move up and it will move down. Alright, so it does one complete up and down oscillation in 1 second. Alright, so this is the period. So whenever we have a displacement time graph, the useful information that we can gather from a displacement time graph is the period. So once it does a one full oscillation, one full up, all the way up to the maximum displacement, back down, that is called the period. Now, I'll introduce the definition of period in a few more slides, but a displacement time graph, it is useful for you to know that I can identify the period of a wave. Now, in a displacement distance graph, the useful information I can gather is the wavelength of the wave. So what is a displacement distance graph? So if a displacement time graph is you tracking just one particle over its whole motion, a displacement distance graph is a snapshot or a screenshot of all the particles in its current position at a certain point in time. So it's as if I took a camera and I took a screenshot of it. Alright, so the useful information that I can gather from a displacement distance graph is the wavelength. Alright, so the next one. So points above the rest position in a displacement distance graph is above the rest position is shown as a positive displacement, below is shown as negative displacement. Alright, so again, displacement distance, the useful information I can gather is wavelength. And a displacement distance is actually a screenshot of all the particles at a certain particular point in time. Alright, so just to discuss what we talked about, displacement time graph, we can tell what the period of a wave is. So by definition, what the period of a wave is the time taken to produce one complete wave. If you recall, the period of a wave is the time it takes to make one complete up and down motion. So the time it takes from here, it moves here or here. Or if I were to carry on and draw the graph a little bit more, this point here to this point here is the period t. Alright, the time it takes to make from its maximum displacement, upwards displacement, it goes down all the way and back up. That is the period. Means to do one complete up and down oscillation motion, that is the period. Alright, so the time taken for it to produce one complete wave is the same time for one particle to do its full oscillation of up and down motion. Alright, so the period, since it's time, the SI unit is second. The second thing that we need to learn, physical quantity, is frequency of a wave. The frequency is the number of complete waves produced in 1 second. Alright, so the frequency and period are related by this formula, F equals to 1 over T. So just for you to have an understanding of how the formula works, for example, if let's say I have a wave that takes 2 seconds to make one complete wave. That means it takes 2 seconds to make this one complete wave. The frequency, 1 over T, is 1 over 2, which is 0.5 Hertz. Alright, the SI unit of the frequency is called the Hertz, written with a big H and a small z. Alright, so frequency equals to 1 over T, it's half, 0.5 Hertz. So if it takes 2 seconds for me to make one complete wave, that means in 1 second, I am only able to complete half a wave. Alright, so that's the understanding and how this formula works. Again, another example, if the time for it to complete one full wave, complete wave, is 0.5 seconds, it means the period is 0.5 seconds. Using the formula F equals to 1 over T, 1 over 0.5 is 2 Hertz. So that means if it takes 0.5 seconds for me to make one complete wave, in 1 second I will have completed 2 waves. So the frequency of the wave is 2 Hertz. That means I have completed 2 complete wavelengths in 1 second. So that is what Hertz means. Now the final useful quantity that we need to be able to describe when we're talking about waves is the wave speed. Alright, since it's speed, very simply said, the SI unit is meter per second. So you already learned this in kinematics. It's the distance traveled by the wave in 1 second. Now, the formula that we have to know and understand is V equals to lambda over T. Now, it may look like something very new, but it's actually just the velocity formula that you learned in kinematics. So just to refresh your memory, velocity is distance over time. So if I were to say, I set the time to be the time for it to make one complete wave to be generated. So for the time taken for one complete wave, it means the distance the wave must have traveled is one complete wavelength. So therefore, if I just substitute the distance as lambda, which is one complete wavelength, the time it takes to make one full wavelength, lambda is the time period T. So that's how the formula is obtained. Now, the more common version of this formula is the V equals to F lambda, which is frequency times lambda. Easily derived from this formula by substituting F equals to 1 over T, which is the formula you learned just before this. Alright, lambda over T, I just separate out the 1 over T. 1 over T by definition is frequency, so my formula becomes V equals to F lambda. So you need to be familiar with these two. Now, just be careful whenever you deal with formulas involving F equals to 1 over T, V equals to F lambda, or V equals to lambda over T. Everything here needs to be in SI units for it to work. Alright, consistent units. Now, Alright, the last physical quantity that we need to be able to describe is the wavefront. Now, definition of a wavefront is here. It is an imaginary line that joins all adjacent points that are in phase. Now, this sounds oddly similar to the definition of a wavelength, but it is different. So, I want you to have just a look at the form at this video here. So if I were to look at water waves, alright, this point here and the next shortest distance here is defined as this wavelength. So where I'm moving the cursor here to here is the wavelength. So waves move as a big mass sometimes, water waves. So this point here and the point just directly next to it, these are adjacent waves, adjacent points, and these points are in phase. So if the wavefront is described as this whole line here, is usually the crest of the wave or the trough of the wave. This is a wavefront. So for example, this here is a wavefront. All points adjacent that are in phase. The trough could also be the wavefront of a wave. The crest here is another wavefront. Here also all is a wavefront. So all of these are wavefronts. It's an imaginary line. Alright, so theory-wise, we have covered everything we need to know about general wave properties. So a few things, I thought it'd be good if we can end off with a little example of a question, possible question that may appear. So let's look at the question. A wave in a string is traveling to the right. So again, I always do this because it makes it simpler for me. I draw a big arrow to indicate the direction that the wave is traveling. So from left to right. And it's traveling at a speed of 2 meters per second. The diagram shows the displacement distance graph. Remember, what is useful information I can gather from a displacement distance is the wavelength. Alright, and this is a graph showing the position of the particle at t equals to 0 seconds. So now they ask us to sketch the graph to show how the wave will look like at t equals to 3 seconds. Now, the wave is moving at 2 meters per second. 3 seconds later, the wave will have moved 6 meters. 2 meters per second, 3 seconds, 6 meters. So you just imagine this point, whatever point P is at, it will now be 6 meters away to the right because the wave is moving from left to right. So I know the position of point of this crest here. This crest will have moved to over here. So when we deal with questions involving waves and where I have to actually draw a wave, I will highly recommend that you mark out the distance from the rest position with a dotted line. So just find the crest, then just draw a dotted line across so that all your waves, all your crests are at consistent height. The same goes with the trough. Make sure you just draw a dotted line to indicate working lines, but then draw it so that your trough are all at consistent length. So again, we go back to the question. P has now, this point, the crest here has now moved 6 meters from 2 meters away to now to 8 meters. So I know the position of P. This fella here, in the same argument, will have moved 6 meters away. 0 meters, at a point of 0 meters, it will now be at this point. So I indicate it easily with just a small graph. So I know that the axis ends here, but if you imagine the wave actually is, there's still waves over here. So here is actually at the position that it will move 6 meters away. So 2, 4, and 6. So that's why I put an X at this position. This fella here at the rest position here will move 6 meters away. Again, 2, 4, 6. That's what I do. I put an X over here. So I do all these X's because it makes my life a bit easier when I draw. So now you can see what the wave will actually look like at t equals to 3 seconds. So all I need to do now, if they ask you to draw on the same axis, all you need to do now is to just connect the dots. And you're done. This is what the wave will look like at t equals to 3 seconds. So just do a quick check and make sure that this fella actually moves 6 meters away, because 3 seconds later, 2, 4, and 6. Yes, correct position. Well, this fella here should have moved 6 meters away again. 2, 4, 6. So now it's at this position. So just basically displace this whole graph 6 meters to the right. Alright. So also it's important, they ask you to, the second portion, they ask you to label the position of P and Q at t equals to 3 seconds. Remember, this is a transverse wave. P doesn't actually move along towards the right by 6 meters. Only the crest of the wave move. P actually executes its own periodic up and down motion. So if P was originally here at t equals to 0 second, and now the wave is over here, so this is the position of P, because P can only move up and down. Since the wave is now at this point at P in its periodic motion, I can identify that this is the position P. Q, same argument, it only executes its own up and down motion. So find the position of the wave, it's here. So this is where Q is. So the answers revealed. Alright, so our argument that we did is correct. It's exactly the same. P is at the rest position, Q is at the position of the trough. Look at the question. P is at the rest position, Q is at the position of the trough at t equals to 3 seconds. Alright, so the final example we cover before we end off the video. Transverse wave is traveling to the right, 2 meters per second. Displacement distance graph is shown below. And they ask you to plot how the P and how the Q, how the displacement varies with time. So just the first thing you should always do is moving to the right. So I always draw a big arrow at the top to show me the direction of the wave. Alright, so the next instant I need to know how the wave will look like. So if it's moving from left to right, all I do is take the original waveform and shift it just slightly to the right. Now just be a little bit careful. It's a common mistake for students to not read this. Sometimes actually the wave is moving from right to left, and you have to just draw the original waveform slightly displaced to the left. So in this case it's to the right. All I do, draw a wave slightly displaced to the right. I can identify where P is moving, I can identify where Q is moving. So just zoom in a little bit. P in this instance is going to move down to this position. Remember, they can only move up and down. Q is going to move up from the rest position. So the answer shown here again, P, the full line is moving down. P is moving down. So all you need to do is draw a periodic wave motion. At the highest instant where P is, it starts to move down, then it will complete one full oscillation and move up. Q, original position, is at the rest position when it's not being disturbed, and it is moving up. So that's how you draw the waveform. Q at the rest position, when it's moving up, it moves up to the highest position, goes back to the original position, lowest position, and then back up here. So this is what it looks like. So just to summarize what you need to do, the notes for this are found on Google Classroom already. Watch this video, do worksheet 13 of your theory workbook, and finally I'm going to push out another SLS package to help you, to serve as another form for you to learn about things. In case you find the video not clear, then you can finish the package on the SLS so that you can also solidify your learning on this chapter. Alright, so have a good June holidays, stay safe, but also study as well. Thank you.